Okay, friends. During the break, as often happens, some interesting questions were asked. I learned that the study guide 10 doesn't actually have you read the section of chapter 10 that's about synthesis. That may have been an oversight on my part, or alternatively, it could be that I made a mistake. I don't know. What I'm trying to communicate to you with this synthesis stuff is just how you put reactions together. None of these individual reactions is really that new today. If you go back and look at each of these, you've seen something like this before. This is an SN2 reaction with different players, but it's a nucleophile attacking a primary alkyl halide, and the leaving group leaves. So that's sort of chapter 7 stuff, right? Acid-base chemistry, deprotonating an alkyne, that's chapter 2 stuff. Another SN2 reaction, that's chapter 7. Bromination, this double elimination of a vicinal dihalide to give you the alkyne, followed by deprotonation. We've not ever done two E2s in quick succession, but the concept of an E2 reaction is not new. So you can connect that to things that you've seen before. And then, getting from the alkene to the vicinal dihalide, that's something we just introduced in chapter 10, like last time. And then finally, getting from an allowed starting material to that alkene is another E2 reaction. So each of the individual pieces is something that you've seen before. What we've done so far has been me basically showing you different Lego pieces. And now we're putting them together to make something totally new. And the new thing is scary and unfamiliar, but that's why we broke it up into simpler parts. If you want more practice on synthesis and you're struggling to put these pieces together, there is a section in chapter 10 on synthesis that you can look at. I didn't require you to do it because I thought we would be okay with just what we talked about in class, but if you need a little bit of extra preparation there, you can go back and look at that. Either way, I would say try some synthesis problems and then go back and read what you need to be successful there. The other thing is just, in what format can you expect a synthesis question on this exam? The most common would be I give you a starting material like this and a product like this, and then I say, which of these options does it? And so you get to choose among various options. So that's different than trying to generate all of this. But it requires the same level of mastery because if you're just vaguely familiar with the reagents, I'm going to get you on some reasonable looking distractors. So for example, what you would expect to be on a problem like this might be, okay, I'm going to start with that alkyl halide. I'm going to use a strong base to make the alkene. Then I'm going to use Br2 to make the vicinal dihalide. Then I'm going to use 3 equivalents of sodium amide to give me the acetylide anion. Let's see, after that, I'm going to bring in this. And then I'm going to need to remove the other proton from the alkyne, and then I'm going to bring in that, and that will give us the product. That's a whirlwind summary of what we just did at the very end of the last hour. There are going to be other options here that are going to attempt to distract you. So what might one of the wrong answers be? Well, suppose I tried to use methoxide, sodium methoxide as a base. Is that a good idea or a bad idea for this first reaction? Bad idea because this is a good nucleophile in addition to being a good base. And what you learned in chapter 7 and 8 is that under this situation, the SN2 product would happen, not the E2. Okay, so that's just an example of something I would throw in there. It would look reasonable, And if you're just looking for reagents that you vaguely recognize are going to pick that answer, it's gonna be rough. Tricky, yes. But I disclose some of my tricks in advance, right? Okay. So, with that in mind, we're going to move on. And I know you don't want to know anything about stuff that's not on exam 3 yet, right? Because you're worried about exam 3. But looking ahead to the future, the final exam is coming, and so there's more stuff to learn. And I'm sorry. So what we're going to do in chapter 11 is to talk about oxidation and reduction chemistry. And we're going to define oxidation in a similar way, well, maybe in a different way than you learned in general chemistry. In general chemistry, you learned that oxidation was the losing of electrons from some material, whereas reduction was gaining of electrons to some material. And that's true. But it manifests itself in organic molecules in a way that's a little bit easier to understand, a little bit easier to follow. So we're going to see that oxidation in organic chemistry leads to either one or the other or both of these, an increase in the number of carbon heteroatom sigma bonds, not necessarily just sigma, will just be general bonds. And in parentheses, Z here is a heteroatom. Heteroatom, meaning is a nitrogen, an oxygen, a halide, sulfur, basically anything more electronegative than carbon. Another type of oxidation could include a decrease in the number of carbon-hydrogen bonds. All right? Reduction, in contrast, is going to decrease the number of carbon heteroatom bonds and increase the number of carbon hydrogen bonds. So that's how you're going to recognize oxidation versus reduction. And we'll talk about carbon-containing compounds. Let me just draw a few of them. Okay. Let's rank these molecules here in order of increasing oxidation. So, which is the most oxidized of these compounds? Carboxylic acid. You recognize that because why? 3 bonds to oxygen. Okay, so it's not just that it has 2 oxygens, it has 3 bonds to oxygen. Okay, and then what? Then the aldehyde. Why is the aldehyde higher up in oxidation than the alcohol? 2 bonds to oxygen versus the alcohol, 1 bond to oxygen versus the alkane, no bonds to oxygen. All right. So, and actually, well, yeah. So if we were ranking things in sort of increasing oxidation state, the arrow in this direction to go from alkane to an alcohol, or to go from an alcohol to an aldehyde, or an aldehyde to carboxylic acid, you would need to do oxidation. But if you wanted to go the other way, you would need to do reduction. Okay? And it's useful to recognize oxidation reactions because you're going to need a special kind of reagent to do that. You need to use a reagent that's capable of increasing the number of carbon oxygen bonds. All right? So down the most reduced types of molecules are alkanes. And, these are hydrocarbons that we get from fossil fuels. And one of the most important things that's done in the chemical and chemical engineering industries is to convert these fully reduced alkanes that you get from fossil fuels into simple molecules that are slightly oxidized. But of course, you don't want to oxidize all the way, because the highest oxidation state of carbon is CO2. And you can do that very easily by combustion, and that's just burning the alkane. But that's not necessarily synthetically useful, and it's bad for the environment. So the chemical industry looks for ways to convert alkanes into partially oxidized versions. Okay? So within each go ahead.
Is that why ethanol is like an additive in gasoline?
Is that why ethanol is an additive in gasoline? Well, with ethanol, what you're doing actually is you're letting other organisms do the oxidation for you. So we don't have a lot of good processes for fixing CO2 and converting it into lower oxidation states. We got a great process for ammonia. We got a great process for fixing nitrogen, the fully oxidized form of nitrogen, into ammonia. That's important for fertilizing, and you can go read about something called the Haber-Bosch process, which was developed in Germany by the same guy that also developed a lot of chemical weapons and mustard gas. But honestly, the Earth could not support the 7 to 8 billion people we have today without that process of fixing nitrogen into ammonia, which we use as fertilizer. In any case, we don't have a good industrial scale process for converting CO2 into like an alkane or an alcohol, and people are working on that. So in this department, Professor Stowers is working on that, and Professor S is in collaboration with some other groups working on that. It's an important problem. The ethanol that we get that's added to gasoline is probably from biological sources. You can ferment any number of things and get ethanol, and so it's a potentially renewable source of those resources. Ultimately, the carbons in the ethanol that's in your gasoline would come from CO2 through a plant, and then a bacteria has to metabolize it and convert it to ethanol. So, yeah, good. Others? Yeah.
Go up. I noticed you left those two out to the side.
Yeah.
Which would be more oxidized, the OH with the hydrogen or the OH with like the extra carbon?
Yeah, what about increased carbon-carbon bonds? You would say that this probably is more oxidized. The secondary alcohol is probably more oxidized than the primary alcohol, at least at this carbon, because there's fewer CH bonds.
What about with the outer carbons adding more? Like with the extra methyl group?
Oh.
The 3 hydrogens being added.
That's true, and the question is, well, how does that affect our comparison? It's kind of messy. What I will say in terms of chemistry is, if you want to convert ethanol into this alcohol, you usually have to oxidize to the aldehyde first and then do another reaction to go from there to there. So Yeah, carbon bonds versus carbon hydrogen bonds, that is a form of oxidation, but not really one that we're going to compare. In other words, I will not ask you which of these two is more oxidized. But of these three carbon alcohols, which is more oxidized? Yeah, ketone, right? So within each oxidation state, you can do a lot of chemistry to interconvert things, right? So I have a lot of easy reactions like PBr3 or whatever. I can turn this into the alkyl halide or the chloride or the tosylate. By an elimination reaction, I can convert into an alkene. So within each oxidation state, there are a lot of what we'll call sort of functional group interconversions where I'm not changing the oxidation state. But then going up from an alcohol to an aldehyde is an oxidation step. We will see that you can interconvert an aldehyde. Let's see. I think we've maybe made the point. The carboxylic acids you can interconvert to acid chlorides or esters or amides without changing oxidation state. Aldehydes you can convert into something called the hydrate without changing oxidation state. You can convert it into something called the acetal, which you won't see till 352. Though we won't learn it here, the aldehyde is roughly at the same oxidation state as the alkyne, which is roughly at the same oxidation state of the vicinal dihalide. And you could even put epoxides in this category, but most of this is just general familiarity. But what we're going to learn, we've already learned a lot in 351 how to do these kinds of reactions, functional group interconversion. And we've included the alkenes here. So that's basically a lot of chapter 7, 8, and 9. Oxidation chemistry you've just barely been introduced to, though you didn't realize it at the time, in bromination of an alkene. That was actually an oxidation reaction. We're going to talk about so 351 involves sort of this area. Interconversion of carboxylic acids with these other groups is an issue of 352. Converting an aldehyde into a ketone is an issue of 352. And a lot of these reactions with aldehydes are also an issue of 352. But in 351, we're going to learn how to go from the alcohol to the aldehyde to the carboxylic acid. And alternatively, we'll learn how to go from the secondary alcohol to the ketone. We're also going to learn how to go from the alkene to the alkane, from the alkyne to the alkane, and from the alkyne to the alkene. So those will be the reduction reactions. So this isn't the last time you're going to see reduction chemistry. There'll be more of that in 352. All right. So with that overview, yeah.
How are we counting so many molecules that don't even have oxygen as one of the highest levels of oxidation?
Okay, so molecules that don't even have oxygen, how are they sort of equivalent?
Like the alkyne.
Yeah. And, comparing the alkyne to the alkane, we could say that basically the reason we're saying that the alkane is more reduced than the alkyne is because of the number of carbon-hydrogen bonds. So our criteria for oxidation is either an increase in the number of carbon heteroatom bonds or a decrease in the number of carbon-hydrogen bonds. So it meets this criteria here, not necessarily the first one. Yeah. Okay. So let's talk reduction first. So what I'm going to show you is a new reaction that it'll be new reagents you'll have to remember, but you won't be responsible for the mechanism. So if you take an alkane, let's take the alkene, or sometimes to avoid confusing myself, I will just say olefin because it doesn't sound like alkane. Those are interchangeable terms. Olefin is from the petrochemical industry. Chemical engineers typically call these things olefins. In any case, you can reduce this alkene or olefin through a process called catalytic hydrogenation. So you use hydrogen, which is a gas, and what that does is it reduces the alkene or the olefin all the way to the alkane. Sometimes we'll call the alkane saturated. It's fully saturated. It has as many carbon-hydrogen bonds as possible. One double bond we will call unsaturated. These terms are actually used. You encountered these terms years ago when reading labels on food when you were bored while eating. You saw things like unsaturated fat, monounsaturated, polyunsaturated / saturated. What those terms meant, it was referring to the number of double bonds in the fats and oils in the various food products. Okay, so how does this reaction work? Palladium is a transition metal. The slash indicates that what we've done here is we have ground up palladium metal into little bits and immobilized it on charcoal, which is just carbon. All right, so you buy this in a bottle, and it's a more stable form of palladium metal. So you have little bits of metal that are microscopic bits of metal that are immobilized on a charcoal surface. And then you add hydrogen gas, or H2. The reaction here is thermodynamically favorable because you're replacing a pi bond with a more stable carbon-hydrogen sigma bond. However, the reaction is slow without a catalyst. And what the catalyst does is it helps break apart the hydrogen-hydrogen bond, and then it helps add the hydrogens individually to the carbons. The mechanism of this reaction is pretty well understood, and it's described in your text. It's not important enough for us to talk about. But let me just say that it occurs on a surface. So I don't know, we'll use little gray spheres for the surface of, or little gray circles for the surface of, you know what, that's a waste of time. Let's just beef it up there. Ah, yes. So you have this metallic surface, and what the surface does is it breaks apart the hydrogen-hydrogen bond. So you end up getting palladium hydrogen bonds here on the metal surface, and then you end up having the alkene or the olefin sit down on the metal surface. And I don't know, you can push arrows sort of any way you like, but the effect is you make a new carbon-hydrogen bond there, and then the pi electrons pick up a hydrogen there. So we don't need to worry about this mechanism, but the idea is the alkene actually sits down on this metal surface, and the two hydrogens are added from the same side. So in terms of stereochemistry, that's not an issue here. These aren't stereocenters. But technically, this is a syn addition of H2 across a double bond. Okay. How does this work practically? How do you get hydrogen gas in a flask? I'll just draw the setup for you. You have this round bottom flask, And at the bottom of the flask, you have the palladium on carbon. And then you have your solvent, whatever it is. And then you have a stopper in the flask, but you insert a needle through the stopper. And then to that needle, you attach a balloon that has hydrogen gas in it. And that provides atmospheric pressure of hydrogen, pushes the hydrogen in here, and then the hydrogen can dissolve in the solution and get down to the metal. So if you were to walk through many of the organic labs upstairs, you would see a setup kind of like this. There are other ways to do it, but that's sort of the traditional one. Okay, so that reaction works for alkenes. It also works for alkynes. So if you start with the alkyne, you can similarly use hydrogen and palladium on carbon to reduce the alkyne all the way to the alkane. Now, it's hard to measure out specific amounts of hydrogen because it's a gas. We just go to the hydrogen tank and literally fill up a balloon, not too big enough to pop, and then we stick that on the needle on the top of the flask, and that's usually enough to drive the reaction to completion. In general, we're using a vast excess of hydrogen relative to our starting material. Because of that, the alkyne goes all the way to the alkane. Some have asked, well, what if you just added one equivalent of hydrogen per mole of your alkyne? Could you stop at the alkene? The answer is, first, I don't know, maybe, but you can't measure out one equivalent of hydrogen very easily. And then the second answer is the palladium catalyst is reactive enough that it's going to, once you form the alkene, it's going to reduce it right away. So even if you tried to measure out one equivalent of hydrogen, as soon as you formed alkene, if the reaction wasn't complete, some of that alkene would go all the way to the alkane, and you'd end up with a mixture of products. So instead, we just use an excess of hydrogen and we go all the way to the alkane. Do you see how that's a reduction in the sense that we're increasing the number of carbon-hydrogen bonds? All right. Now, what if we wanted to stop at the alkene? What if we wanted to reduce the alkyne to the olefin? Is there a way to do that? And there are two strategies for that. The first is to continue to use hydrogen, but we're going to use a modified catalyst. And this is a proprietary catalyst called Lindlar catalyst, named after the person that invented it. It is palladium on carbon, but there are additives that slow down to an imperceptible pace reduction of the alkene to the alkane. So you can take an alkyne like this. You can add hydrogen gas, use the Lindlar catalyst in a similar way, still with the balloon, and you will reduce the alkyne to the olefin, but you're going to get the cis olefin, the cis stereochemistry, because this is a syn addition of H2 across the pi bond. All right. So that's one way to stop at the alkyne, or stop at the olefin from the alkyne. You're going to have to memorize this fact because I'm not explaining to you why the Lindlar catalyst can stop at the alkyne. I've said this is just a way of remembering it. It's still a palladium catalyst, but you've added some stuff that prevents the further reduction of the olefin to the alkane. So that part, it stops at the olefin, you're going to have to memorize. However, if you remember that this catalyst involves palladium metal, then hopefully your mind will be drawn back to this idea that it still occurs with the alkyne approaching a metal surface, so both of those hydrogens get added from the same side, and if that happens, then yes, you do get syn addition of hydrogen across one of the pi bonds of the alkyne. All right? So that's an example of a stereoselective reaction. We exclusively get the cis isomer. Questions about that? This part of the class is hard because in many of these cases there aren't mechanisms that we ask you to learn. So you're left with sort of memorizing what a reagent does. And so you're going to need to practice. Now, if we can make the cis olefin, one question would be, can we then take the same alkyne and instead get the trans olefin, where the hydrogens are added to opposite sides? And the answer is yes. And your strategy here is going to be to not add both hydrogens at the same time. Right? If you add them both at the same time on a metal surface, it's got to be cis. But if you add one after the other, then you can form, there's a chance that you can form the more stable trans stereochemistry. So what are the conditions here? This is called the dissolving metal reduction. I mean, it sounds somewhat fanciful. The dissolving metal reduction of an alkyne. What is the metal? The metal is sodium. And to avoid confusion with Na+, I'm just going to put a 0 here. This tells you that this is sodium metal. All right? So that is the metal that gets dissolved. What does it get dissolved in? This is sort of bizarre. Liquid ammonia. Ammonia is a gas at room temperature, and so you have to actually generate the ammonia liquid first by condensation on something cold. You have to keep your flask cold. And there are, how this occurs practically is not that big of a deal. But what ends up happening when you put sodium metal in liquid ammonia is the sodium metal actually ejects an electron into the solution. You didn't know that electrons could dissolve in solution, but in this case it can. Likely it's not just the electron on its own, but rather it probably is the electron surrounded by ammonia that are stabilizing the negative charge with ion-dipole interactions, right? Each of these hydrogens is less electronegative than nitrogens. So you can use the electron-poor hydrogens in ammonia to sort of solvate the electron. And the cool thing about this is that situation has a color, and it's dark blue. And so if you look up the dissolving metal reduction and look for images of it, you're going to see a flask filled with a very deep, dark-colored liquid. And so if you ever wanted to know what color an electron was, that's not the actual color of the electron. That's just the color of the electron in ammonia, but it's kind of cool. What does this do? Well, the electron, when it's dissolved in ammonia, can now add to the pi star of the alkyne. The process that happens next is summarized in your text, and I don't care that you know it. But along the way, there are intermediates that are negatively charged, and the protons get added sequentially, and so you end up getting the more stable trans product. So this happens by sequential addition of an electron and then a hydrogen atom and an electron or a hydrogen ion, a proton, and sequentially occurs an electron and a proton and then an electron and then another proton. And where do we get these protons from? We have negatively charged intermediates that deprotonate ammonia. The details are not important, but the fact that it's sequential gives you the trans isomer. All right? So we have some versatility here. We can, if we want, take the alkyne all the way down to the alkane. We can also reduce it to the olefin, and we have methods for getting the cis olefin and the trans olefin. This is a nice way to expand. Well, suppose we can now use these reactions in tandem with some others to really test your understanding of stereochemistry. So one of the questions could be, if I start with this alkyne and I do the dissolving metal reduction of the alkyne to give me the transalkene, and then I do bromination of that transalkene, what is my product? And being able to follow through the stereochemistry there and contrast it with what happens if I simply do hydrogen and Lindlar catalyst to get the cis-alkene, and then I brominate, then what happens? And the two situations, the two products from the first set of reactions and the second are going to end up being diastereomers of each other. So it would be good for you to sort of predict the products here and follow through the stereochemical issues associated with these reactions, and your two products should end up being diastereomers of each other. Of course, if you make a chiral product, you'd have to have both enantiomers. And I will put the answers to this in the notes so that you can see it. Okay. The last reduction reaction we will do today, and this will conclude reduction for us, is going to be something that's actually not that new. It's only a new reagent, not a new reaction. Opening of an epoxide. And I'm going to put this in. Now they're air quotes. I guess they're not air quotes when they're on the page. I'm going to put that in quotes because we don't use H- as a nucleophile. H- you can't buy on its own. You buy it in an ionic compound with sodium. That's called sodium hydride. And sodium hydride is not that soluble in organic solvent. When you do reactions, it's like it sits in a chunk at the bottom of your flask and you stir it around and it acts like basically a huge sterically hindered base. The hydride ions are never free enough to attack carbons as nucleophiles. So we don't use this as a reducing agent. Because it's insoluble. And so what we need is a reagent that is soluble in organic solvent and can deliver the hydride to the desired reactive place. We need a hydride delivery reagent. So I'm going to introduce one today. It's called lithium aluminum hydride, and you will encounter it again and use it more extensively in 352. Lithium is the positively charged counter ion. For a lot of these reactions, the counter ion does matter, so lithium has some interesting properties which we don't need to talk about, but that's why we choose that counter ion. Then aluminum hydride is aluminum bonded to 4 hydrogen atoms. Aluminum, like boron, normally comes with 3 valence electrons. It currently owns 4, so this is going to have a negative formal charge on it. But just like we talked about earlier today with hydroboration reaction, aluminum is less electronegative than hydrogen. So the negative formal charge on aluminum is actually more accurately depicted as partial negative charges on these hydrogens. All right, so we're going to see aluminum do what we saw boron do in the hydroboration reaction. It's going to deliver H minus to a reactive center. So if we had an epoxide, and let's say it was this epoxide, aluminum hydride would act as a nucleophile, and it would deliver, it's going to act as a strong nucleophile, and it's going to deliver hydride directly to the less substituted carbon of the epoxide, because it's a strong nucleophile. Hydride isn't leaving and floating around. This is a direct handoff of H minus from aluminum to carbon. Regioselectivity is just as we learned for epoxide opening in chapter 9, in that the good, strong nucleophile under negative charge conditions is going to choose the less substituted carbon. And then after an aqueous workup where we add water, we protonate the alcohol, and we end up with this product. So what's new here is not epoxide opening. Opening of an epoxide is a chapter 9 reaction. We've just introduced something else you can use to open an epoxide, and in this case, it just delivers H minus. All right? Okay, that's reduction. Go ahead.
So last, when we did opening epoxides before, so that would technically be reduction as well.
Yeah, it counts as reduction because your nucleophile is H minus, and you're increasing the number of CH bonds and decreasing the number of CO bonds. Mechanistically, it's just SN2. Yep. Other questions? All right, it's a tough part of 351. It's a tough part during a regular semester. It's even tougher during a spring semester. I'm sorry, I feel for you. I'll pray for you. Good luck.